This video
Another
is
video
about solving problems involving a ramp or inclined plane.
So this one is from the practice problems, question number 9.
So this is two-dimensional
motor and
forces
chain are used
problem
to
because we have
pull
an
a heavy
angle.
object up a ramp, as shown.
So some of the
Coefficient
forces
of
will be
friction
in
for the
two
surface
dimensions
is
here, and some of them
0.4,
just one
that's
dimensional.
mu.
The angle is 22 degrees. That's theta.
So an object of 9.3
Tell us
kilograms
the mass
rests
of
on
the
an
object
inclined
is
plane.
362
The angle of the ramp is 23 degrees.
Find the minimum
Find the
force
magnitude of the
required.
friction
So
force.
that'll be our applied
So
force
notice the object
from
is at
the
rest.
motor.
It's resting on the inclined plane.
So the motor is pulling.
So
the
we know
object
some of the
up
forces
ramp.
are equal and
Find
opposite
the minimum
because
force
there's
of
no
the
acceleration.
applied
The
force
object is
required
at rest.
to start the object.
So what
moving.
we do is start with a free body
Constant
diagram.
velocity.
So always
so we
watching
can
out
draw
for,
keywords. If you remember constant velocity,
something
means
like this
that's
for
the
the
net
ramps.
force.
And the angle
will be
is
0.
23 degrees. So there's no acceleration here. So there's our
The
angle.
object
of
is
23
moving,
degrees,
but it's
from
moving at a
the
constant velocity
horizontal.
up the ramp.
We want to find the minimum force required
measure
up from
to
horizontal,
just get
23
the
degrees
object started
angle of the
moving.
ramp. And the
So
object
if you're
is resting on
a note
the
here, right?
ramp.
For
So
an
we can
object
draw
moving up
a
a
free
ramp,
body
friction
diagram for
is
the
gonna be
object.
down the ramp.
The
ramp,
object is moving up the ramp,
and then
it's being pulled up.
think about
so
the
the
friction
forces
is
that are
always going
acting
to
on this
oppose
object while it's at
motion.
rest. So there's always
So we
the
can draw a
weight,
free body diagram to see all the
FG,
forces on this object on the ramp.
which is always
And
straight
if you
down.
remember from the last video, we draw.
So no matter what
Here's
the
our
orientation of the object,
Yeah,
the
the weight
angle
is
always directly
theta
down.
there.
So
we
there's
need
our
that
weight. We also have a
horizontal
normal
surface.
force because this
And then we have our object
object
sitting
is
on
at
the ramp.
rest
Again, the
on a
object is
surface.
at rest.
So anytime
on the
there's a surface, we have a normal force.
So we have all the
and if you
normal
remember from the notes,
typical forces.
the
here.
normal
We have
force
the
is
weight
always
straight down.
perpendicular or
That's
90
FG.
degrees.
We also have a
to the
normal
surface.
force because the object is
So
sitting
our
on a
normal
ramp.
force
A surface.
is here.
So anytime an object is on a surface,
So we have the weight,
and
we have the
remember,
normal force.
The normal force is perpendicular.
We also have friction because we're asked to
surface,
find
90
the
degrees.
magnitude of the friction force.
We also have our friction down the ramp. The
So
friction
we have to decide now which way
is
do we draw the
opposing the
friction.
motion here. So
So if you think about the
our force of
situation,
friction is down.
if
the
the
ramp,
object is at rest on the ramp, and that would be the negative direction,
and we'll make
there's
up the
no
ramp positive.
it's not going to roll
And
down
then
the
if you
ramp
remember from the other
or
video,
move up the ramp. So it's
the first ramp
it's
video,
balanced by
the weight
some
has two
opposing
components
force.
here, X and Y.
So if you
component,
think
because
about
we
if there
have
was
an
no
angle.
friction here,
Same
the
angle
object
of the
would
ramp.
roll down the ramp or slide down the ramp.
So then we draw the X.
So
and
that
Y
means that
component.
friction
So the Y
is
component
opposing the
is
motion or
parallel to
potential
the normal
motion of
force.
this
Just draw a straight line
object.
through.
So we can draw
That's
the friction
our FGY,
Y
up
component
the-
of the weight directed up the
this
ramp. So opposite the direction that the
component
object
here
would
is
move.
the X component.
if there was no
and this is
friction.
always a right triangle.
So we have an angle here. This angle given
So
in the
if we
question,
want to find the
23
minimum
degrees,
applied force
is also going to
required,
be the
we need
angle
to draw the applied force
inside
on
of
here as
here.
well.
So our weight is going to be a
So just use
two-dimensional.
This
It's going to
color.
have a Y
Our
component
applied
and an
force
X
is up the
component.
ramp. That will be positive.
So the Y component is
So the coefficient of friction for the surface is straight 4. That's part
straight
of
down like this.
friction.
You notice it's parallel to the normal force. This would be
If we want the minimum force required here, we need
the Y
to
component of the
always
weight.
do the net force.
And
We know
remember,
net
the only
force is
reason
0, but
the
we're gonna
weight
find
is two-dimensional is going to write out the net
because there's an
force.
angle here, like we always
So we
do.
can make our right triangle like we always do.
So in the X direction,
So we have the Y
remember that
component,
includes
FGY, and then we have the X component of the weight.
In the
down
X direction, we have the X component
Just to
of the
maybe,
weight, we have the applied force, and we have the friction force.
Clean this up a bit.
And in the Y direction,
move
we
the,
only have the normal
FG
force
over to
and
the other side here.
Y component of the weight.
So the
And
actual
the weight
weight
itself is not
vector
X or Y,
is FG.
because it's at an angle. So let's do the
Straight down.
net force,
And
in
then
the X
we have an
direction.
X and a Y component for the weight.
We're looking for the applied force. The
We
applied
need to
force is in
find the
X
magnitude
direction.
of the friction force here. Here's our
So if
friction
we add all the
force. It's
forces
going
in the
up
X
ramp.
direction, we have
So
the applied force.
if this object is at rest, that
We
means
have our friction
If
force.
you remember, that means the net force
And
is
then
0.
don't forget the X component of the weight is also part of
F
our
net
force
equals
is
0
in the
here.
X direction. So plus,
because the object is at rest.
FGX.
So in the X direction, the net force
and we know
is
that this
0.
equals 0
moving along the ramp,
because the
and in the
the
Y
object
direction as well,
is going to be moving at constant
the net
velocity.
force is 0. Because the object
Once
is
we
at
get it
rest,
moving,
anytime the object is at
just
rest,
going to
the
be
net
moving at a
force is equal
constant
to 0.
speed, so no acceleration. So our net force is 0.
So how are we going to find
we're
the,
looking for the
friction
applied
force
force,
here? If
we
we do
can
the
just
net force in
rearrange
the x direction equation here, we add up all the forces that are in the x direction.
So
So
we're
this
solving
is
for
our
applied force, so we subtract the other two.
surface of the ramp is our
So our
x.
applied force will be
kind of our x-axis,
equal and opposite
and
to the
then
friction,
the
and equal and opposite
normal force
to
and the
the
y
x
component of the weight
weight.
are on the y-axis.
So we need to find
So
the
looking
actual
along the
friction
x-axis,
force
we
here
have the
because
friction
we only
force,
know
and then down
the
here we also
coefficient is
have
0.4,
the x component.
and
of
we also
the
have to
weight.
find the x component of
And
the weight.
so if we do the friction,
write
the net force,
formula
it's the
for
friction force
finding
plus
friction
the x component of the weight.
is
And
friction
these are
force equals
going
mu
to be
times
equal and opposite.
Fn,
The net force is
which
0.
is
We know
mu
this
times,
because the object is at rest.
The normal force is equal and opposite to the weight.
So we can write
So
0
minus
for the net
mg.
force equals the friction force plus the
So
y component of the weight.
For the
And if you
friction
remember from
force in our
2D
equation here, we
vectors,
can write
if you're finding the x component of a force, you just take the force
minus mu
and multiply by
Fn
cosine theta normally.
minus,
In this case,
and
if
then
you
to
look at
find
this
the x
triangle,
component of the weight,
if you remember I said ramps are a little different.
component,
If you look at the
it's
triangle,
just the force times
the x component
sine theta
is
in this
opposite
case.
the angle.
Remember for a ramp.
So that would be sine.
Use sine for
So
the
only
x
when you're doing ramps,
only for
the x component
ramps.
is f. So FGX is
Cosine to the
sine
mg
of the angle.
times sine
So
of the angle.
in other words, that's
It's
going to
22
be
degrees.
FG times sine of the angle.
So all we have to do is
23
calculate
degrees.
these two now to get our applied force.
So very important. Usually finding the x component is always cosine, the y component is sine.
So we multiply
If we're going to draw our triangle
mu
like this, and if we want to use the same angle that's given in
times
the question,
m times our mass
Um,
times the
we have
acceleration due
to
gravity.
use sine for finding the x component. So we're looking for the friction force,
So
which
for
is right here in our
the
equation.
friction
And so we
force,
can just rearrange this. So the
It should
friction
be,
force, we're going to
positive.
subtract this piece,
1, 5, 6
is equal to
2
minus FG times sine 23.
25 newtons, and there's some.
And if you remember
there.
FG,
And this also will be
weight
positive.
is
Remember our
m
applied
times
force
g, 9.81
is positive because it's
meters
under
per second squared. So,
So we're
minus
going to just do
FG
m
would
times
be
g times
minus
sine 22,
mg
but positive.
times sine.
So the mass is 362.
So our mass
g is
is
9.81,
9.3 kilograms.
and then
G
we multiply
is going to
by
be
the sine
negative
of
9.81 meters per second squared.
So for the second piece
So,
here, I got
I encourage you to
1,330.
try this calculation on your own.
And then
I'll
we
do it
add
right
these
now.
two together
So 9.3 kilograms
to get our final answer for the
times
applied force.
9.81.
So the applied force.
So this is going to be positive
just
because
add
we have a
these two
negative
together.
number here in front of the mass, and G is also negative. And then we're going to multiply by
is roughly 2,000
sine of 23.
93 if I round it up.
And I get 35.6.
So the
for some other digits.
motor
So
is applying a force of
35.6
2,893 newtons.
for
to
the
get
friction
this object
force. That
moving,
would be
on
positive. We
the
got a
ramp.
positive answer, which tells us
So in this case, when
that
we
it's
have
the
we have
direction
friction on the ramp,
we
we have an object, we also have
down
an
the
applied
ramp would be
force.
negative.
The applied force has to be, the magnitude has to be equal and opposite at least.
If you think about
to
significant
the
digits,
x component of the
last thing I
weight
wanted to
and
say,
the friction. So it
you
has
look
to
at the number of
overcome
digits in the question.
the two forces that are
so there's
opposing
two
it,
digits
and
there.
the weight in the x
We
direction,
have three digits here,
which
so
is trying
the
to
least
pull the
number is
object down
2.
the ramp.
So
and
we're
the
going to
friction.
answer to 2 digits. which
Once
would
you start
be,
pulling the object, you have
could
to
round this to
overcome the friction as well.
36 newtons.
To find the applied
35.6
force,
rounded up
what
to
we needed to do
36.
is find the x component of the
So
weight
the friction
and
force
the
is
friction and add them together.
36 newtons. And that
The
would be
applied
equal
force
and
is equal
opposite
and
to the x
because
component
of
of the
the
weight.
constant
So
velocity
the x
condition.
component of the weight would
That
be
means
negative.
the acceleration is 0.
36 newtons. So these two forces,
So all the forces are equal and opposite.
the x component of the weight and the friction force on a ramp, if the object is at rest, these forces are going to be equal and opposite. So if you know if you can find the x component of the weight, then you know the friction force.